This is problem 95 of Neetcode with 50, min cost to connect points. So we're going to be given a 2D integer array points, and we're going to have x and y coordinates. All right. We know that the distance we care about here is the Manhattan distance between 2 points. So we have to connect all the points in a Manhattan distance. And this final distance has to be as small as possible. So first of all, what is a Manhattan distance? Okay. Um, so if I have a grid like this, and I have a point here, and another point here, well, we know that basically the distance is approximately this, right? And this is going to be equal to, let's say this is 5. But how can we know that from our x and y coordinates? Well, basically, we're going to take the distance that we went through in the x directions, and also the y difference, right? So this is the Pythagoras theorem. So we know that this is going to be 3, this is going to be 4. So this is how we actually solve the diagonal. But in our case, we actually just want to have the Manhattan distance. And in this case, the Manhattan distance will be 3 plus 4. So we will have a Manhattan distance of 7. So that's pretty much it. In our problem, it doesn't make a big difference because if we wanted the diagonal, we will just have to use the theorem of Pythagoras. But now we can just take the difference of the delta x plus delta y, and it gives us the distance. So that's really it. And now let's actually find an algorithm to solve this problem. So let's say these points are somewhere in a graph, and we are starting from here. Okay, so we have to somehow find a way that at the end we have something that looks like this, right? They're all connected by their shortest distance. And I draw like diagonal lines, but technically speaking, it will look like this, right? But just for the example, I think it is convenient to actually just draw the diagonal lines because that's all we really care about is the shortest distance. So to solve this, we're going to use the Primes algorithm. So the Primes algorithm states that when you start from a certain node, like for example here we are starting at the node that is circled up in blue, we're going to go calculate the distance we have to travel to reach all the other nodes. And we are going to pick among all these distance the shortest one. In this case, it is this one, obviously, from the drawings. Meaning that now our pointer is at this particular node that is circled up, right? And we're going to do the same thing. So again, we're going to calculate all the other, its distance from the other nodes. We're going to say that this one is the smallest, so we're going to actually go there. Just like this. And again, our pointer is now at this particular node. Notice that we don't calculate its distance from the nodes that we actually went through before. We will do so by keeping track of those we visited. So we're going to have to create something that will keep a measure of which nodes we visited in the past. All right, so starting at this node, we are here, and now we could go there. We could go there as well. Notice that this path is much shorter, so we're going to go here. All right, so now our pointer is at this node down there. And notice that from here, the only node we haven't visited yet is this one. So we're going to calculate its distance. But actually notice that from this path, we have quite a long distance to travel where from the previous node we were at, we can go directly to that last node in a shortest path. So we're gonna have to find a way to actually go back to this node. So put our pointer back to this node, go travel here, and from there we're gonna go see all the nodes that haven't been visited yet, and we'll see that there's only one node that has been that hasn't been visited. So we're gonna calculate this, and finally go there. So that might be seen as a tricky part, basically, to just readjust our pointer, but you'll see how we do that in the code in a quite optimal way. So from what we can see now is that for each nodes, we're going to calculate its distance to all the other nodes. So basically, we're going to have a time complexity of n squared. And in terms of space, well, we are going to have a space complexity of big O of n, because we're only going to keep track basically of the what has been seen. So we're going to have a measure for that, and also for the distance. And that's pretty much it. So it's going to have a big of n space complexity. And notice that we have 5 nodes, right? And how many edges do we have? We have 1, 2, 3, and 4. So this is good. If I say that E is edges, we know that the edges will always be equal to n, which stands for the number of nodes, minus 1. All right. So keep this in mind. This is a pretty pretty important concepts of trees and graphs. Well, especially trees. So let's go ahead and code this solution. All right. So first thing we're gonna have to I will keep a variable I will call n that will hold the length of the points. And I also want to have nodes, because the nodes will be called from 0 to n minus 1. So I will make sure that we are going to start at the node that is 0. So I want my n basically to be just the length of the point. So how many points do we have, which stands for how many nodes do we have. And the initial nodes we're going to start with is going to be node 0. Now I want to keep track of a distance, and you will see why a little bit later. But this is going to be basically the foundations of how we can adjust our pointer to the node that has the shortest distance from the remaining nodes. So basically, I will create a very huge distance for each nodes. We know that each nodes are from the value 0 to n minus 1, so their value can be used as the index to refer to their distance inside dist here. So this is basically going to be, I will actually say infinity, right? So it's going to be infinity times n. Great, so now each values have currently an infinite distance. And I just want to do this because what we want to do is that we always want to check that the new distance is smaller than, right? We're trying to find a shorter distance. So it makes sense to start with the greatest value possible, so that whenever we hit the first distance, it will actually become the distance, because it will be smaller than infinity. Now we want to have a scene here, which is basically going to be whether or not we saw a particular node before. This is important because otherwise we will have an infinite loop at some point. And basically it's going to be false times n. So we know that we haven't seen any of these nodes so far. Remember that the number of edges is the number of nodes minus 1. So I want to keep track of these, because this will be important for my while loop. And I just made a mistake here. So I will keep a measure of the edges, and also the basically the total distance we have so far. Both will be initially equal to 0. And once I have this, I can actually use my while loop, and I will do my while loop while the edges is smaller than n minus 1. So now you can see the importance of this edges function. So the first thing I want to see inside, the first thing I want to do inside my loop is basically set the scene at the node we're going to pass to true. Then I want to keep a measure of the pointer, and the pointer, it's basically the next node, right? So let's call this next node. And what value can we give to that next node? Well, we know that at the end of this iteration, we're going to have to point to the value of an actual node, which is between 0 and n minus 1. So we can really give it any value inside the negatives. It will work just fine as first, because um, we just want to set a pointer that is, well, exactly like we did with distance, something that we know we will eventually change once we hit um, an actual node. All right, so now we can actually go see all the other nodes. So we're going to say for I in the range of n, and this is where we want to calculate the distance from that particular node we are at to the other nodes inside inside our 2D board. All right, so what we're going to do first is that if basically we saw this, so if seen at this index, so if this is true, well, we're just going to continue because we don't want to create an infinite loop. We're just going to continue. And after this, we will create the current distance. So the current distance is the Manhattan distance, which is the difference, well, the delta x plus the delta y. So all we are going to calculate this. I will use the absolute value of both. So ABS for the delta x and ABS for delta y, and actually this is a plus sign. And what I want to do is I want to go take the value inside the list points at the index I, which is going to change, and basically the second index 0, so we can get the x values, because the values are stored as a list containing like x and y. So we're initially going to take the x values, and we're going to subtract this to the x values of the node, like this. And now for the delta y, we are going to do the same thing, but instead of taking the index 0, we're going to take the index 1. So this is going to give us the y value within each list. All right, so just like this. So that is the distance that we're calculating for each node to the other nodes. All right, but we want to keep track of the shortest distance, right? So what I will do is that I will set, remember, in our dist here that we created. So the distance at that index I that we are at is basically going to be equal to the minimum between its current value and the current distance. So that now we know that once we, let me just erase a couple of things here. We know that when we are here, we'll have to keep track of a certain value of that distance here. So let's say this is 4. So whenever we are here at that last node, and we know that we only have one unseen node, we're going to calculate that. We're just going to check if the distance to that particular node here, which is going to be at that index I, is this distance, I said this is 7, is this smaller than that? If it's not smaller, actually go back to here. Well, go back to here, so move your pointer, and then go see the other nodes that are unseen. All right, so this is how we're going to do that. So now we're setting that distance I to the minimum of both. All right, and after this, we're going to set our pointer to that smallest value. So first of all, if the next node, if this is equal to -1, well, we know that for sure we want to move that, because otherwise, if we never move it, and we find a node that has, well, if we if we have an error or an edge case where we just have no nodes, we're eventually going to point back to -1. So we want to make sure that we're going to move it if, well, we want to make sure that we update the next node if it is pointing to -1. And basically, the logic here is that if the distance at the current index I is smaller than the distance at the next node, well, we want to make sure that we update that next node to that index I. So this is how we move our pointer. And that's the entire code actually um, for the while loop. Um, well, for this for loop, because after each of these rounds, um, we're gonna add to the results basically the distance of the next node that we are visiting. So we know that this next node is containing the shortest value that we add in this particular case. We're gonna set a node to be that next node. And finally, we're gonna add the edges. So we're gonna add one to the edges because we created a link, and this is really important to for the while loop. All right, and after this, we're gonna keep looping inside this while loop, and once we break this, it must means that we have basically connected all the dots with the shortest distance, so we can return the results. And let's test this code. And it works. Awesome. So I hope you learned from this video, and I hope to see you in the next one.